Hi everyone, welcome everyone to the IEEE webinar. And today we have Professor Steve Korns. He is going to give a talk on computational intelligence for disaster planning and mitigation. And I would like to take this moment to advertise next webinar, which is autonomous bootstrapping of collective motion behavior for swarm robots, which will be held on 22nd of February. So if you are interested, you can register for that. So now, please welcome Professor Steve to this webinar. So you can start.
Thanks, Bethany. So welcome everyone. The swarm robots does sound interesting, so I might be a recurring customer here. But today I'm going to talk a little bit about disaster planning and disaster mitigation using computational intelligence. So this is actually an area I've been working on for several years, along with one of my co-researchers, Dr. Susanna Long, in our department, and a lot of different graduate students, more than I can really name here. So this is kind of a body of work, and I'm pulling some different pieces out of it just to highlight some of the things we can do with computational intelligence and how they can fit in to this particular area of research and how we can try to benefit society with it. So a little bit on, let me get to the slides, a little bit on disasters. So what type of disasters have we looked at? We are pretty much neutral on what disaster we're actually looking at. So we'll do earthquakes, floods, hurricanes, tornadoes. We've looked at a lot of these things, but they share commonalities. So there's damage to property. So this is an old picture, the San Francisco earthquake, 1906. So yeah, it's over a century old, and it caused damage, and we learn lessons from this, right? So now we have buildings that are resistant to earthquake. We have those around Ring of Fire, if you will, around the Pacific Ocean, Tokyo, California. So that adds benefit, less damage, less risk to people. But we have other events as well. So this is actually from a storm that has gotten a lot of press, but this isn't one of the areas you've really heard about. So this was Hurricane Katrina back about 16 years ago. And this is Biloxi Bay. So New Orleans wasn't the only area that was really hit hard by this storm. Hurricanes are huge. So a lot of damage to infrastructure. Obviously, this is not a road that you're going to be driving on. So how can we actually look at predicting things and maybe preventing damage from that? Or something a little closer to home. If some of you may recognize the St. Louis Arch there. So this is the Mississippi River, St. Louis, Missouri. And this is one of the flooding events that we've had in recent history. You can see down at the bottom here, there's actually a road. And so that road is underwater, impassable. And this isn't even one of the worst flooding events that we've had in this area. So there's a lot of different disasters. All of these require different approaches for how you would actually try to prevent infrastructure from being lost, personal damage, or probably worse, loss of life. So in these extreme events, as I'll call them just in general, there's an immediate danger to human life and property/infrastructure. So people's lives are at risk, things are being damaged. Everybody's familiar with, you've seen the movies with buildings falling over, very dramatic. Well, in Hollywood, it's very dramatic. It's very stressful. There's a lot of things going on, a lot of different infrastructure elements, transportation, electrical, water. So going in and restoring these or trying to mitigate damage to them becomes a very complex problem, especially urban environments, also when we start stretching out into the rural areas. So we need some tools that can handle large amounts of data, a lot of different interactions. And this is where computational intelligence comes in. It gives us the ability to look at a lot of different inputs and try to figure out what's going on and how we can relate that to the particular issue that we're dealing with. All right. So one of the immediate things is direct economic impacts. And we can try to prevent things like that if we know that a disaster is coming, or if we know what's going to happen in a particular area, we can try to build up our defenses, if you will, strengthen buildings, harden architectures. But there's also indirect economic impacts. So damaged infrastructure costs money to repair, but if we don't have a transportation network, we don't have our supply chain, that causes other impacts. And we call these indirect impacts. So yes, the bridge is damaged and we have to pay to fix the bridge, but while that bridge is out, we can't ship goods across it, people can't go across that bridge, and this causes other impacts. So now we have delays in goods being supplied. We have people not being able to get to work in time. So we look at all these things. How do we mitigate it? How can we try to keep it from happening or restore it after it's happened? So to frame it a little bit, because I'm making the broad assumption, I guess you could say, that these things are complicated and it takes a long time to fix. So we'll go back to Hurricane Katrina. So this is from 2009, the photo at least, and they're reporting on the 2009 time, even though this is a 2014 article. 9 years after Katrina, that was a 2005, so yeah, this is 9 years after Katrina. Coastal restoration plans remain a distant dream. 10% of production capacity is still not operational. So that's 9 years after the event. I did a little bit of digging. Washington Post last August did say that some areas have fully rebounded while others still have storm damage. I leave in this point, they did say overall the city has bounced back well since 2005, but that's been 16 years after a storm event. So that shows there's a lot of pieces moving around. There's a lot of damage that was done. So we need some way of dealing with this. Now, I was saying that we are disaster agnostic, if you will, but a lot of this work was funded by Missouri Department of Transportation, and they were wanting us to look at flooding and how flooding affects roadways. So I'm going to focus on that a little bit. It's Missouri Department of Transportation, so we're going to be looking at Missouri, although you could extend this to other areas. We have two different types of flooding that we're going to look at initially, and we're going to tie these things together. We have, in the case over here, just flooding, floodwaters, rivers rising, coming out of their banks. So this is also an area of interest that we're going to look at, but you can see the impact on the transportation network. All these semi trucks lined up, trying to get through Interstate 44 is what that road is. And then the underpass is completely filled in with water. So this has happened a couple times within recent memory in the state of Missouri, at least 2 times in the last 15 years. So they are changing the infrastructure there. They're making overpasses, but how do we predict when something like this is going to happen so that we can reroute? Then flash flooding. Flash, by definition, is a quick event, so it's harder to predict than actual flooding, but it's very localized. It can be damaging in that small local area, also a threat to life, but it requires a little bit of a different approach to how we get the data. So again, flooding and transportation is the major concern that we're looking at. So it's a common extreme event in Missouri. Again, the Mississippi River down by the arch, water levels rise, roadways become topped, also rails can become topped. Trains are very large, there's a lot of momentum, but you still don't want to drive them through water, because the water levels topping these roadways start becoming a risk to public safety, transportation flow. You can't see whether or not something's washed out under these roadways. So this is one of the big dangers that we're trying to predict. I'll get into a little bit more detail of what they advertise as a danger, but turn around, don't drown is one of the sayings they use. Getting to a point and trying to decide whether or not I should drive through this water that I have no idea how deep it is not something we want people to get to. So we want to avoid making people have to make that choice. So St. Louis is also interesting in that if we look at the different waterways around it, we have the Mississippi River, we have the Missouri River, And then we have the Merrimack River, which is smaller, but it's still sizable, especially where it meets the Mississippi. All the major roadways cross a bridge over one of these rivers other than, and this is Highway 100, which is 4-lane in some places, but it is nowhere near the capacity of what these interstates are. So if there's a major flooding event that takes out these bridges or an earthquake, then St. Louis becomes an island. And this is one of the major points of transportation for the supply chain. So it's of interest to try to anticipate what's going to happen in this area. It does have a large impact on not just the people in the local area, but people across the United States. So how can we tell if one of these bridges is going to be at danger of having to be closed or maybe roads over top? So how do we do these predictions? So river stage is one of our major indicators along with discharge. Discharge is the water going through. River stage is how high the water is. So that gives us an idea of at what height the water is going to be downstream from it. There's also an impact from what's the water level upstream, downstream. All of this is going to affect our water level. So right now we have 6-hour predictions. Some of the work is done by Army Corps of Engineers, some of it's USGS. There's a cooperation there, but we have 6-hour increments. If we think about driving and figuring out if a road is going to be topped, 6 hours is a very long period of time. It's hard to make decisions with that level of data. So we want to improve the predictions, but also improve the prediction rate. And neural networks seems to be a good fit for this. It's a function approximator. There's some function that's going to describe how the water level changes. Now there's early information, early time step information. It's going to tell us how things change. We can look at historical data. So it is going to be time dependent. So we chose a long short-term memory for this. LSTM is one of the more popular methods for deep learning right now. I'm going to go into a little bit of detail. Some of you may not be familiar with it. So I did want to cover a little bit of what we're doing with that. So long short-term memory. It's a deep learning algorithm capable of learning long-term dependencies. Long-term dependencies become important if there is some effect that's happened before that repeats or some previous information that we need to make a different decision later on within the algorithm. So remembering other patterns, having a way of actually storing that in memory becomes important. So it's made up of a series of cells that retain learned information, and it has a methodology for passing this information through. It has the ability to select information that it's going to forget or remember at different points through the algorithm or through the network, which is similar to a recurrent neural network. It's actually a modification of those recurrent neural networks. So I'm going to assume most people have heard a little bit about neural networks, but I will go into recurrent neural networks. So recurrent neural network is a network that uses its output as an input for the next stage. So typically you're going to see this arrow coming through here indicating, well, it's actually the output gets looped back to the input. So if there's a time dependency, this gives us some kind of memory. So some memory of what's happened at previous stages. When it was introduced, this was the first time that we had that memory built into a neural network, and it gave us ways of actually not starting from scratch every time when we tried to learn these dependencies. So this representation, you're going to see a fair amount, but a little bit easier way of understanding what's going on is if we kind of unfold that. And you'll see this a lot in some of the literature. So we have our regular input to our neural network. So that can be different sensor data, historical data, whatever our inputs are. And we map that to some kind of output. And that's through a typical training process. We look at what do we predict based on the output or on the input. Was our output correct? We figure out what the error is. We adjust the network to reduce the error. So that's your standard neural network, but we also have this input from previous states. The way this is drawn, and I just took this from other normal representations, you don't see the time dependency, but there is a change in what we're passing forward each time. That gives us a way of remembering, well, what did we predict at some previous state? But it's a fairly straightforward, usually there's just one layer of a neural network within each one of these because we have to train each one of these. We have a large network. So back before we had all these high-powered graphical processors so that we could put our networks on it, this worked well, but it had issues. When we start training this, there's an issue called a vanishing gradient. And the training got more and more difficult because we had so many different pieces that we had to adjust what the weights were, how we actually predicted these outcomes. So around 97 or so, some researchers, Hochreiter and Schmidhuber, came up with long short-term memory. So like I said, this is a modification of the recurrent neural networks, but it replaces each one of these nodes, these H's here, with a multi-component unit. So it is the overall cell that has the processing of the input, the output, looking at the memory from preceding units, so handling those different pieces. There is a method for removing information, so a forget gate. And that allows us to take things out of memory as we move forward through whatever we're analyzing in our network. There's also an input gate so that we can add information. So we have different ways where each cell can modify what information it keeps a hold of, what information it gets rid of. So what's important at that particular point in the algorithm. And then there's an output gate, calculates the overall output. So similar to a lot of other neural networks, although the calculation is a little bit different. So if I walk through each one of these, this is our overall cell. So some similarities to a recurrent neural network. We have our input. We have the actual prediction. We take the prediction from a previous state. We pass it on to the next state. And that's also our output for what we have at this. I'm going to use a generalized term and just say time step. So if I'm predicting what is going to happen in the next 15 minutes, I output this current 15 minutes, I pass it forward, the next cell looks at what happened, and it's predicting what happened in the next 15 minutes. So the cell kind of holds all that information, but we also have a state, a cell state, and that's the information that we're keeping in memory. So we have previous state information as memory, but we also have a cell state as memory. So what are the things that we need to keep a hold of? So the forget gate, we have a sigmoid function here as a squashing function. So it takes the input, it takes a previous state's output, and it determines, based on that, what information do we need to get rid of, or what information should we forget about? So this is just shorthand for, we take the inputs, we apply weights and biases. That's our typical neural network methodology. And that passes a vector of information that it should be the same size as the state vector. And it passes it up to that function. Now we also have a method for adding information, our input gate. So similarly, we have a sigmoid function. It looks at the inputs, determines, so what things would have value to be added to our state memory. We also have a hyperbolic tangent function, and this is more of a analyzing the inputs and coming up with the results. So we have some different inputs. All these are different vectors, same length. So how do we add this into our state memory? So if we look at the cell, we want to update our cell state using this candidate information and the information of what's valuable there. I'm going to refer to it as a mask. We have the same thing with what we're going to forget. So we have a vector from 0 to 1, values from 0 to 1 that we're multiplying by this state. And that's how we update the cell state. So we have a pointwise multiply here. What happens is this vector is multiplied by the cell state. If the value is 1, we keep it in memory. If the value is 0, we remove it from memory. So each state is multiplied, pointwise multiplied by the vector that we came up with from our forget gate, so that if it's a 1, we keep it in memory, 0, we remove it, and that's passed forward to our next point where we're adding to memory. So now we did the same type of masking where we have an output from our hyperbolic tangent. So that's going to be from -1 to 1. We mask it based on what are the things that we think we should add to the memory. And that vector is then added to our cell state, so added to our memory. This gives us a way of updating the different points within our cell state. We can remove here by multiplying by 0, or we can add to it, which if we think about this, this is a vector. This is from -1 to 1. We multiply it by something that has a value from 0 to 1. So that's going to give us values from -1 to 1, right? We add that. Now we can have values greater than 1, less than 1, depending on what those outputs are. But that also reinforces the memory. So updating that, we can now do an output. So the cell state's been updated. So the cell state's the cell state. We already determined that. But now we look at the inputs. This would be our output element. So weights times the inputs and the bias. And then also we're looking at a squashing function for what we have in the cell memory, and we multiply it by that. So this will give us information about what we saved in the memory, and this will tell us what actually is important in that. This provides us an output, which moves forward to the next state and also is reported for the algorithm. So that's a very rough, very plain vanilla LSTM. There's a lot of information out there if you guys are interested in this. It works very well for time series data. It's also very good for natural language processing, things that there is a dependency on things that happened before. So it's pretty effective. It worked well for us. So it's out there available. Highly recommend it. So what do we do with this? I have this gathered together like we did all of this at once. This is actually a body of work where we use different elements at different time. We added information to try to improve the accuracy of the algorithm. But looking at what we're trying to predict being gauge height, so what is the water level in these rivers? We look at the previous time steps gauge height. So that's an input since we have that data. We look at the current rainfall. We also can look at previous rainfall. That's going to tell us things about ground saturation. It's going to tell us things about how much water is flowing into the river. We look at gauge height upstream, downstream. This is one of the later pieces that we added. But if there's more water upstream, that water is going to come to you downstream, correct? If there's more water downstream, there's going to be resistance to having the water drain off. So all these things are going to affect your water level. And then geospatial data for rainfall catchments. This is basically, if I look at some kind of river system and I have a stream flowing into it, it has all kinds of little tributaries, just drainage ditches, maybe storm sewers, things like that. That is your catchment. So any of the water in this area, when there's rainfall, is going to flow into the river area. How fast is going to depend on things like change in elevation, average change in elevation, how many streams there are, the lengths of these streams. So all this information is available in a software package called ArcGIS. So it has all of our geospatial information, but it's not directly related to, say, an equation where we could calculate that. At least that's not the approach we use. So we used a fuzzy C-means clustering to see what in general were the commonalities between these. And then we used a numerical value assigned to it based on the cluster. So this is the data that we put into our LSTM, which is how we predict this gauge height. But that's just one piece that ties into it. If you're looking at any of our computational intelligence techniques, they do a great job at predictions, at classifications. but there's other pieces around it that we have to start pulling in to be able to use that to inform the public, industry, whoever we're working with to get our final answer. So we developed this framework for transportation. Data acquisition, getting all those gauge heights, the information about river levels, rainfall. We pass that through our LSTM to predict gauge height. And we get some kind of result. This is actually one of our snapshots of it, how we actually predict what the changes in river level are. Then we have to pass it into this, we'll refer to it as a flood inundation profile. This can be information from the ArcGIS. Also, Army Corps of Engineers has this tabulated in a website. We can pull in this information to figure out what happens, what changes on the water level based on these gauge heights. What's at risk of flooding? Then we can overlay that onto a road network, figure out what roads are closed, figure out how we're going to reroute people, or when we're going to warn people don't go this way because it's going to flood. And that gives us an idea of how we can reduce indirect costs, or what the indirect costs incurred are going to be. So the data. We accumulated data for this intersection, which is the intersection I showed you earlier. I-44 and Missouri Highway 141, frequently flooded. Heavy traffic area. Interstate 141 is also a fairly significant highway within the area. We have historical gauge height data. This green point here is actually where they have one of those monitoring devices. So it sends in gauge height data every 15 minutes, but we don't get a prediction of what the flood level is going to be every 15 minutes. And this was one of the pieces that kind of made us scratch our head a little bit. We have 15-minute increments of data, but the actual prediction of flooding was on 6 hours. So starting May 19th, 2016, onward, we had a large number of data points. So we go up to September of 2019. And this is the overall results we got from our LSTM. So there's a blue line in there that you can hardly see. There's a couple, we had a large excursion here, which we didn't catch. Excuse me. You can see some other blue, especially on our peaks and valleys, which is kind of typical. But overall, the training went very well. Testing, we validated the testing against this output. The overall result, a root mean squared error of about 0.45, which was much better than what the current predictions are from the USGS. So overall, we got pretty good results. This was the error only in the testing region. So there was an improvement. So yes, I mean, that's what we always put in our papers, right? We did better than. So more accurate is good. Now we also had the same increments that you have with the flood stage, but it doesn't tie into that flood prediction. Same increments we had with the river gauge. So how do we actually tie that into flooding? So that was Army Corps of Engineers. Our flood gauges are USGS, and you see they have a lot in Kansas City, a lot around St. Louis. They're trying to expand this, but it gives us points where we can look at, if I look at this map and the water level gets to a certain point, and you can move this slider on their website, it shows you what is going to be underwater, which is a lot of fun and interesting and all this stuff. And we look at the gauge heights, and it tells us what the discharge is and all these identifying numbers. But what we get from that is we say action stage height. This is for the Merrimack River. It's within the banks. Everything looks pretty good. We get to 16 foot. Now we start seeing some water coming out of the banks in other areas. 19 foot, it continues to be a little bit swollen. 25 foot, now things are getting flooded. And we see a lot of water in these different areas here where water's not really supposed to be. I guess that's actually okay, that's a lake. But we do have water backing up. So now we're looking at, if I have water at this 25 foot level, what road is going to be closed? And we could probably go through, look at this and guess, well, these roads are in danger, but it would be nice to just automate the process to tell us what road is in danger of being flooded. So again, same picture. That is this intersection. This is significantly higher than this 25-foot gauge height. So if we have something like this, which is 54 foot, how is it going to affect the roadways? And we can look at that from the flood inundation map, and you see a lot of blue, right? So the flood inundation mapper tells us this information. We can pull that in. The raster means it's a raster layer. That's an ArcGIS reference, but it doesn't tie into the roadway because the roadway is a point layer that looks like this. But we can automate some manipulations. We can look at where they intersect, and now it shows us here are the roads that are going to be flooded at a particular water level. So now we have some way of looking at the different roadways. We can pull that out as a graph network showing the roads. So we look at the different vertices in this graph. We look at the edges, which edges have to be removed because of flooding. And that gives us a way of reporting these flooded areas. So that's some of the processing that we do with it. And this gives us a way of trying to figure out some early warning. So we have weather data. We pass it into our flood models. We update the road conditions. And this is done every 15 minutes. If they aren't going to flood, we keep monitoring. If they do flood, then we relay to these warning messages. They have signs in different places, warning flooding ahead. They can send it out to automated messaging systems to update maps and to tell people this area is going to be flooded. We're currently working with integrating it into an app that we can tie in with some of the different GPS. I don't want to use a particular company's names, but navigation software, so that we can update those as well. Determine what the new route is, update the routing algorithm. That way people don't drive up to a flooded road and have to figure out whether or not they turn back or if they try to go through it. So that was one of the major things we were looking at. We don't want people to have to put themselves at risk, but also the transportation network. How can we reroute that to try to minimize delays? Because all those delays, time is money, right? So flash flooding. We looked at flooding, so it was kind of a natural follow-on to, well, how about flash flooding? It is a danger to infrastructure, but it's actually more of a danger to human life because flash flooding is a quick event. Neither one of these pictures is actually flash flooding because it happens within a couple hours. You don't have this steady rise, you know, upstream. We have water levels coming up, so we have a lot of forewarning about flooding. No way to stop it because it's a huge amount of water, but we have a warning. We can develop those warnings a little bit better. Flash flooding, it's a little bit harder. There's no high water level necessarily, but it's a very localized, large amount of water that just can't be drained off quickly enough, and then it overtops roads, sometimes just washing vehicles off of the road, which has happened and is very dangerous. So how do we predict these? We use some of the similar inputs. We look at rainfall for that day, the previous 3 days. We look at the geographical information from the GIS software again. But to actually do training for our network, now we have to figure out when was there flash flooding events. So when did these things happen? And to do that, we have to pull in some historical data. So rather than what was a previous state, now we're looking at what did it look like previously when this happened. So fortunately, NOAA, which is National Oceanic and Atmospheric Administration, they have this database with all kinds of different events and stuff. So we were looking at, in this case, Greene County. Again, working with Missouri Department of Transportation, USGS was helping us, a lot of different folks. But now, since it's flash flooding, this happens in a different part of Missouri more often. So now we're looking at Greene County, and we can pull up information on flash flooding. The problem with this is these are all narratives. We have times when it happened, we have location, but now we have to look at what roadway was involved. And Here we can see Greene County areas that flooded were low water crossings and low-lying areas. Other locations that are affected by flooding included Ward Branch Creek in Springfield, a section of Highway CC 2 miles west of Fair Grove. So we have to be able to pull the language out of this. We did not automate this. This was actually graduate students going through, looking at the data and pulling it out. Later on, future work, maybe this is a good opportunity for natural language processing. But this is how you can get that data so that you can try to predict whether or not a flash flood occurred. So I talked about the explanatory layers. This is the different change in elevation, the direction of slope, curvature of slope, different things about the geography in the area. So we got a lot of this from the US Geological Survey's national map, and this also tied in with ArcGIS software. This is one of the big tools if you're looking at any of the topological data for US and also other countries. So there's data available for all kinds of different things. This is your Google Earth type stuff, right? Even though I just said I wasn't gonna use particular names. So we can pull on that information and we can look at, in this case, Greene County. And this is one of the particular areas of the hydrology. So one of the drainage areas. We have locations that did have flash flood based on the NOAA information. We have areas that have similar type of information but did not have flash flood events. So this gave us a way of having more of a balanced data set. So now we can look at this, we can figure out what the information is, and now we can do a classifier. So we take our data, we have different rainfall, antecedent rainfall, all of our different geological or geographic information. We train it, we come up with different prediction methods, support vector machine, neural network. We also looked at logistic regression, and we came up with a classification model and determined what the results are. So the neural network did pretty well. These are a little hard to read, but 40 of the not flash flood, that actually was predicted correctly, 35 flash flood predicted correctly. Support vector machine, a little bit less, but comparable. Logistic regression really didn't do as good predicting true on there was a flash flood. So the deep learning did a little bit better, but support vector machine still does pretty well, is pretty good as well. I should also note you can adjust different probabilities of whether or not there's an 80% probability, a 70% probability. So when we use a neural network, we use an output that gave us a percentage. So we were using a I think it was just a multi-layer a very large number of layers on the neural network. It wasn't really convolutional, so it's not like your AlphaGo type architecture, but it was several layers. And so we come out with a value from 0 to 1, and that we could use as a percentage, anything 80% or higher, 70% or higher. So we could use that as a risk indicator as well. So that gave us a little bit of an idea of the flash flooding prediction. Not too bad. If we adjust that percent probability, we can reduce a lot of the, well, we said it wasn't flash flood, but it was. And those are the dangerous events. So we could kind of control that a little bit. So we looked at a lot of the flooding. So we're trying to predict when they're going to happen so we can reroute, or we can put up sandbags. We can try to protect the different infrastructure, the property. But what happens if we already had an extreme event occur? Some things are harder to predict, such as earthquakes. I talked about those a little bit. Missouri, I don't know how common knowledge this is if you're outside of Missouri, but there is a very large fault line in the state of Missouri. New Madrid Fault is one of the things that we look at. If that were to have a large earthquake, then it could affect a lot of the areas in St. Louis and different parts of Missouri. So earthquakes are actually a concern in Missouri. Then also a lot of the areas that most people think of, California, Japan, a lot of different places around the globe that are going to be affected by this. But it's harder to predict an earthquake. So now we're looking at, if it happens, how do we restore it? We can use this also to, if it happens, this is going to be the cost, this is going to be the damage. So what would be the value of hardening this infrastructure? And we can use that for decision making. So if we look at different infrastructure elements, and that's what I'm going to focus on here, like bridge restoration. The restoration is a fixed cost, but we have these indirect costs. And I talked about this a little bit earlier. Interstate transportation, road and rail, not being able to get goods from point A to point B. Local traffic, not being able to get around. There's the obvious, not being able to get to a hospital or medical care, which is important, but also not being able to get to work, not being able to go and provide the different things necessary to support local infrastructure, local industry. So all these things are going to have an economic impact on the area. So these are going to be direct, excuse me, indirect costs, and they're going to be incurred until those repairs are actually made. So looking at when do we repair different parts of the infrastructure is going to impact what the overall cost is. Excuse me for a moment. A little bit of a cough there. So we're going to have these costs for, in this case, bridge restoration until we finish restoring those bridges. So I'm going to look at St. Louis because, like I said, it's kind of an interesting area. There's 3 major rivers, there's 4 interstates, there's 31 different bridges, which makes it at least something that's not a trivial problem to solve. And again, we have Mississippi, Missouri, and Merrimack. So the circles are different bridges. The color is which river they're actually crossing. We have our different interstates. This is Interstate 70, this is Interstate 64, this is Interstate 44, this is Interstate 55. And all of these interstates also go across the river. Now there's also bypasses, there's 270, there's these different spurs, but all of these have bridges going across the different rivers. So if there's a major earthquake event that takes these bridges out, St. Louis becomes an island. Very difficult to move goods in and out of St. Louis. We're looking at mainly air transportation. Now things are very expensive. So for this part of the overall body of research, we're looking at determining the order using an evolutionary algorithm. So I've historically done a lot of work with evolutionary algorithms. They work well for these types of problems. They don't care about nonlinear relationships. The parameters, you just put them in there. They're very scalable. We could move this up. We could try to capture every bridge going across the Mississippi. It's going to affect convergence time, how long it takes the algorithm to determine a good answer. But we can increase the scale. If we compare this to things like linear programming, we start running into a lot of issues with the number of variables that we're looking at, especially if there's any kind of stochasticity involved. So it gives us a way of looking at these different problem solutions. I'm not going to get into a whole lot of detail on evolutionary algorithms, but there's also information available out there. So the cost for restoring the bridges was used as a basis for indirect costs. If we look at a bridge, all the bridges have a particular length associated with it. There is the 2 points where they're attached to the ground or the other roadways or whatever we're looking at. So those abutments have a particular cost. The length has a particular cost. Each one of the different pieces you have those different supports is going to add cost. And then you have the superstructure, the roadway itself, the deck, if you will. All of that has a cost associated with it based on length and width. So number of vehicles that can go across. This is also going to be indicative of if you have more lanes, you can get more traffic across, right? So this gives us a relationship between the cost to restore the bridge and how much traffic that we're allowing to now move back and forth by restoring it. So there's a relationship between the restoration costs, the bigger bridges cost more to restore, but they also, based on that width, give us more ability to move goods and people. So there's research done by Inky et al. I can share that paper if you're interested, that relates this direct cost of the bridges to the indirect costs incurred. And it's somewhere roughly around 50%, although that's not the exact value that they use in the paper. So when we look at the evolutionary algorithm, we look at what is the indirect cost, but we also rewarded infrastructure connectivity. So how much of the area are you reconnecting? If you're having a bridge go over the Mississippi River, then that's going to connect everything on the east side of the Mississippi to this area. If you're doing something that's only crossing the Missouri River on one of the interstates, we're still missing out on the entire eastern side of this problem, where now if you're doing the Missouri, it is more or less the northwest part. So that was part of the fitness function that we used that was rewarded, the number of river crossings. So how many bridges did we restore across each river? If we had 5 bridges restored and they were all over the Mississippi, that wasn't as good as, say, 2 bridges over the Mississippi, 2 over the Missouri, and 1 over the Merrimack. So alternating that has value. Then the number of lanes crossing the bridge, restoring that infrastructure, was also valued. So all this goes into our fitness evaluation. How good is this solution? And we compared this to a greedy algorithm. The greedy algorithm was just trying to restore as much as possible. It was forced to alternate between the rivers. So we gave actually one of the bridges over the Mississippi, we said would not be brought down because it was argued it can withstand up to 9.4 on the Richter scale, I believe. So that one we assumed was a given, so that bridge will remain standing. So the enforced alternating was Missouri, then Merrimack, then back to the Mississippi. That way we don't have the greedy algorithm trying to restore things and be at a negative because it doesn't recognize that part of the fitness evaluation. Even so, the evolutionary algorithm had a better indirect cost reduction, about 12.4% compared to that greedy algorithm. So it performed pretty well. Again, it was only 31 bridges, but if you expand that, then you could look at an overall supply chain. You could look at different areas, consolidate things. However you develop your transportation network, we can identify points, right? So if I were to, say, zoom out and look at the entire United States, I could treat St. Louis as one point, even though there are multiple pieces in there. And then you can look at solving for the entire supply chain infrastructure. So this gives a way of looking at how do we adapt, what do we do to try to restore it at the most effective pace. It could also give us what if scenarios. So what if we had this event? Could we maybe take one of those bridges going over the Missouri, strengthen it like we did that Stan Musial Veterans Memorial Bridge, if I remember, is the one that was hardened. So if we reinforce one of these bridges, is that going to give us a return on investment? So we can use it for decision making for mitigation plans as well. So overall, in conclusion, the LSTM, the deep learning mechanism, gives us a lot better predictions that we can feed into these model frameworks. Again, we looked at comparing about a 0.45 error to over a 1 R estimate, root mean squared error. So a lot better prediction. It also put together something to where we can get predictions more timely. Also giving information about where flash flooding may occur, both the flooding, the flash flooding, gives us a way of warning the public earlier, tying that into public announcements, makes it to where the traveling public is safer. We could also look at increasing supply chain recovery. So If we reduce the time, we reduce indirect costs, or where is our best point to invest into hardening the infrastructure? Where are we going to suffer the most losses if one of these events was going to occur? And then that tells us, if anyone's familiar with your Pareto analysis, it's where's the most bang for your buck to put this investment. So finishing up, acknowledgements, Missouri Department of Transportation funded a lot of this work, but there was also a Department of Transportation Transportation Center, the Mid-America Transportation Center, who also helped fund this. We got a lot of cooperation from U.S. Geological Survey, a lot of data, also Missouri State Emergency Management Agency updating us with different ways that they manage this, National Weather Service, National Oceanic and Atmospheric Administration, all of our rain information ties in with all that information we got from the Geological Survey on roadways, Army Corps of Engineers, the flood inundation mapper, all the different gauge type information. And then, of course, my home department, all the students that we were working with, the faculty I collaborated with on this. So all of this was a multi-year large body of work, but you can see some of the benefits of being able to make these types of predictions, figuring out what these results are going to be. So it's about 8 minutes left, I guess. So if there are any questions, I guess we're going to put those in chat.
Okay, there are some questions. The question is that, have you worked on this research? Hold on, I can see it. Wait a minute. Sorry. Okay. The question is that, have you worked on this research on model explainability in terms of what caused those predictions to occur? This is the first question. And the second question is that, are policy-making organizations requiring this? I don't know.
Okay, so the first was, have you worked on expanding the size of the models, basically?
No, I think he asking about the cause that this prediction can occur. I mean, in terms of expandability thing. I don't know.
Expandability of the methods.
Can you explain the model? Yeah.
So if we look at the flooding prediction, if you had a network of, now Iowa has a lot, you have a flood center, which has a lot of predictions about water level heights as well. Sharing that information, expanding this type of work, and then if we can share that information to update a broader map of what the impacts are going to be. Also, there's the issues of levees, things that protect different either farmland or cities from flood damage. If one of these were to fail, then that's going to cause water levels to start rising downstream very rapidly, but still predictably. So if we could add that, expand it to capture those types of events, that's something that did happen in the state of Iowa, just north of Missouri, I believe 2 years ago, and caused a lot of damage. If we could have tied that in, most of the damage was in the state of Iowa, but if something like this could have been tied in, then I think we could have, we're not going to save the property, but we could have warned people. We could have evacuated maybe a little bit quicker.
Okay, and the second question is that, are policy-making organizations requiring this? I mean, explainable model, I guess.
Yeah, so our policymakers using this, this is actually something that we have in front of state of Missouri right now, talking about using some of these things. Policy is a slow-moving thing, right? The wheels turn slowly.
Yeah.
So they are aware of it. We've been sharing this information both through the Department of Transportation and other channels. We do meet with the Emergency Management Agency for the state. So whether or not it goes into policy, some of the SEMA, State Emergency Management folks, do know it's there, it's available to them. Part of this is also that app. in the integration of the results from this body of work into your navigation software, but also into, I'm not going to try to bring up a web browser because usually it's bad to do that.
Okay.
Sideways. But Missouri Department of Transportation does have an updated map showing where flood events are.
Mm-hmm.
And so
Mm-hmm.
that gets tied in with some of that notification as well. Policy, hopefully, but it is available to those agencies.
Okay. Okay. I don't see any other question. Keely said, thank you. It's a good talk. That's what Keely said. Okay, next question. I got a question. What are the technology limitations in terms of collecting aftermath aerial data for situation awareness?
So aftermath, that's usually pretty tricky because depending on what timing you're looking at, we focus largely on restoration. Restoration being the rebuilding after the event. If you look at that, then there's surveying, you can do flyovers, we can look at, you can create a network of the transportation systems and looking at, it might be satellite information if the satellite flies over it, and probably would be for a restoration time frame. You can look at what are the changes, technology there, you could look at image recognition and overlay that to determine changes to your network. And I'm just going to speak to restoration because the whole rescue type phrase, it's very difficult to get information. You just try to update the information as quickly as possible.
Okay. And I don't have any more questions. Okay, he just said thank you.
All right.
And I don't see any more questions, so I think we're gonna end it here. Thank you so much, Steve, for giving a wonderful talk.
Yep. Thank you for the opportunity, and thanks everybody for coming. If you do have questions, you can get a hold of me through IEEE CIS. I think they have my name out there somewhere. BBTC, if nothing else, my name is on that technical committee.
Okay, and the record video will be posted to this webinar system and also IEEE CIS YouTube channel. So if you want to catch up later on, you can look at the video later. Okay, thank you so much, Steve, for coming, and it's pretty nice talk. And I'm gonna go to sleep now. Good night, everyone.
All right, take care. Thanks, everyone.
Okay, take care. Bye.